So now we will continue with equivalent circuit and the electromechanical relations. So already we sketched the equivalent circuit here, and now we will try to do the proof for the electromechanical relations. Okay, so first we need to find an expression for the EMF, then we will find an expression for the torque of the machine. So to find an expression for the EMF, we start from the equation E equal to B LV sine theta, and this is the voltage generated per one conductor. Okay, so we will call it as EC. So we will write this as E conductor. And as we mentioned before, that theta will be 90 by design. Okay, so sine theta will be 1, and you are collecting the maximum voltage or maximum torque, and this is by adjusting the angle between the brushes and the poles or the magnets or the flux. So if you have a conductor or a wire, and this wire is subjected to flux, and you start to move this wire with a velocity v, a voltage will be induced according to the right hand rule. So I will receive the flux into my hand. This is the flux. This is the direction of the velocity. So the EMF will be in this direction. So here we will have negative and positive E, and this is E conductor. This is the EMF per one conductor. So the EMF per one conductor will be PLV, as sine theta, as we mentioned, is 1. And we said that we will not construct the machine from just one single wire. It doesn't make any sense. So we will make the machine made from coils, and the coil actually will have number of turns. Okay, so this is a coil. If we go back here, you can see here that this is one coil. You can count how many wires we have in this coil. So this is one coil, this is another coil, and so on. So we put inside these slots, we put coils. We are not putting just a single wire. So when we find the EMF, so the brush will touch one of these coils, and by design it will touch the coil which has a maximum angle or 90-degree angle. So this is the coil. So we need to move from E conductor to E total or E coil. So to find E coil, we will take E conductor, then we will multiply it by 2, because we have 2 conductors per turn. So each turn of these has 2 conductors. So to make one turn, you need 2 conductors. So this is a turn. And then the coil has number of turns. So we will multiply this by n, and n is the number of turns per coil. This will give us our total E. So our total E, which we will name it as E total, or which will give it the name E, will be 2BLV multiplied by n. So 2, because we have 2 turns, and the n is the number of turns per coil. Now, the flux density B is actually the flux divided by the area. And to get the area, if we go back to this shape here, I will copy this. I don't think. Okay, so to get the area, we need the area seen by the flux. So actually, we need to find this area here. So this is the area that we are looking for. Okay, to find this area, so to find this area here, so to find this area here, which is the area seen by the flux, we will assume it is a square. So to find this area, we need to find this depth, and we need to find the length of this arc. And if we multiply these two, we can get the area, assuming this area is a square. So the depth of the machine, we will call it L. So L will be the length of this machine. So let's go to a better image. So the length L will be this length. This is the L. We call this the effective length, which is the length of the coil covered by the flux. So if we go back, so this will be our L. So the length of the coil covered by the flux, this is the effective length. So we will design the length of the pole, which is the depth of this image here, to be the same as the coil. So this L is actually the length of the coil that will be inserted inside here, which is the depth of this pool here. We make the depth of this pool to match the coil length. And if we neglect the air gap, we have some air gap between the two poles. If we neglect this air gap here, and we assume that the two, if we assume that the two poles are touching, if we take the perimeter of the machine, this is the perimeter of the machine, and we divide it by 2, so we will get the length of this arc here. So if we neglect the air gap, if we neglect this air gap, so we are assuming that the poles are touching. So to get this length of the arc, we can take the length or the perimeter of the machine and divide it by 2. So the area here, so the area will equal to the effective length multiplied by 2 pi r divided by the number of poles. So P is the total number of poles. In our example here, we have just 2 poles, so we should divide by 2. But some machines can have more than 2 poles, 4 or 6 poles. So we will make it generic. So the area is 2 pi r divided by P. And the velocity, usually we use the angular velocity, not the linear velocity. So we know that V, or the translational motion, or the linear speed, equal to the angular speed multiplied by the radius. If we put these two relations into the E equation, so the E equation will be 2 multiplied by phi divided by the area, and the area is 2 pi r divided by P multiplied by L. This is multiplied by L, and V is omega r multiplied by N. So L cancels L, R cancels R. So the equation here for E will be, and 2 will cancel 2. So the equation will be P N over pi phi omega. So this is the equation for E. So let's take this here. So it's a Pn over pi multiplied by phi omega. So P is the number of poles, total number of poles. Phi is the average flux per pole. Omega is speed in radian per second, and N is number of turns per coil. Don't forget that once you design the machine, N will be constant, P will be constant, and also pi is constant. So we can write this equation as E equal to constant K multiplied by phi multiplied by omega, and the K is called machine constant, and the machine constant is P N over pi, and it is constant. And you can see that the EMF, the back EMF, is proportional to flux and speed. And this is very important, that the voltage generated E is function of the flux and the speed. Okay, so this is the first equation that we will use a lot for DC machines. This is one of the basic equations for DC machines, that E equal to K phi omega, and we call this the EMF equation. We had a similar one for transformers, if you remember, and the EMF for transformers were 4.44 phi F number of turns. Okay, so we had the same for transformers, for AC circuits. So now we have the EMF equation. So this is the first electromechanical equation. The second electromechanical equation 2 is the torque equation. So what we have for the torque equation, so for the torque equation we will start. So here we have a coil, and this coil is subjected to flux, and assume we have a current I entering in this coil. So the current will enter from outside, go inside the coil, and then the current is going out again. So if you apply the left hand rule, so you receive the flux into your hand, your thumb points to the direction of the force, your fingers point to the direction of the current. So here you will have a force going in this direction. So you will have a force going so let's just take this and try to move it a bit, or let's keep it as it is. So here you will have a force acting in this direction, and here you will have a force acting in the other direction. So here you have F, here you have F. These two forces will produce a torque, which will cause us to rotate. And once this starts to rotate, you will have a back EMF. So to get the torque, we will start from the force, and the force is the force coming from one conductor. So the force coming from one conductor is BIL sine theta, and as we mentioned before, that theta is 90, so sine theta is 1. To get the torque, we will take the force and multiply it by 2, because you have two forces acting on the center, or you take the momentum here, so you will take the force and multiply it by 2r, which is the diameter. So we will multiply the force by 2r, or the diameter of the machine, to get the torque, and we will multiply this by n, which is the number of turns, assuming that you are not constructing the coil from one turn, but actually you will have multiple turns, and all of them are producing forces, and the current is circulating. So the current is entering here, then it keeps circulating in all these turns before going out again to the source. So the torque will equal to F multiplied by 2R multiplied by N. The force is BIL multiplied by 2RN, and B is phi over area multiplied by IL 2RN. Phi, the area as we did before, is 2 pi R divided by P multiplied by L multiplied by IL 2RN. So 2R will cancel 2R, L will cancel L. So we will have the equation for the torque, that the torque, we call it T induced. The induced torque will be P N over pi phi I. And if you remember, this is the same constant that we have it before. Okay, so we can say that the T induced, the torque induced, equal to K phi I. And don't forget that this is the current I going into the coil or into the armature. That's why we name it as IA. And this is the second important equation that we have, which is the torque equation. So this is the torque equation. So the torque equation that T equal to K phi I, and the EMF equation that E equal to K phi omega. Okay, so now we have two important equations for the machine. So we call these as machine equations. So the machine equations is E, and we name it E armature equal to K phi omega. And the second equation is T, we call it T developed or T induced equal to K phi IA. So these two equations are very important, and the K is the machine constant, omega is speed in radian per second, phi is the average flux per pole. This is the flux we have, so you don't have to divide it or do anything. It's already the average flux per pole. And IA is the armature current. So these are the machine equations, and these machine equations are very important. Now look at the following. So we have EA equal to K phi omega. We have T developed equal to K phi IA. Now look, if you multiplied here by IA by IA, and you multiplied here by omega, and you start to compare the two equations. So here you multiplied both sides by IA, so actually you didn't change the equation. And here you multiplied both sides by omega, so you didn't change the equation too. Now if you compare, you can see that EAIA equal to T developed omega. So this part is electrical, and this part is mechanical, and this is called the electromechanical energy conversion equation. So this is the equation for electromechanical energy conversion. So if you have a motor, you are supplying electrical, so EAIA will be converted into T developed omega. So this direction is the conversion for motor. And if you have a generator, you supply an input torque T developed and you rotate it, so it will generate electricity for you. So it will go on this way if it is generator. So this equation is the equation that governs the conversion from mechanical to electrical or from electrical to mechanical. So we name this equation as the electromechanical energy conversion equation. Now we can tell the motor story and the generator story using this equation. So let's see how we can tell the motor story. So the motor story, you start by step 1, you supply current IA. So you inject current into the motor. So if you have a motor, you plug the motor into the electricity. So you start by supplying current IA. So this current IA will produce torque T. And the relation between IA and the torque is that T equal K phi IA. Once you produce torque, this torque will rotate the machine according to the mechanical equations, the Newton's equations or the motion equations. So this torque will produce speed or give you speed. So the mechanical equations, that summation of the torque equal to the inertia multiplied by the acceleration. Okay, Newton's second law of motion. So once you have the speed, so this speed means that the motor will start to rotate and the coils will cut the flux. So you are producing an EMF, back EMF EA, according to the equation EA equal to K phi omega. This produced EA is opposing the current. So this is the reaction against the current, and this is the story of the motor. So you inject the current I, this current produces torque T, the torque will rotate the machine according to the mechanical equations. Once the machine starts to rotate, it will cut the coil cut the flux and produces flux. So it will, cut the flux and produces voltage E, and this E will be the reaction of the machine against the current. So when you have an action, there is a reaction against it. And this reaction has to be from the same nature of the action. So your action was electrical, so the reaction at the end will be electrical. So this EA actually is the reaction of the machine. And to get this reaction, the machine has to move. So you get the motion from the motor as a byproduct. For generators, the story is different. And don't forget that these two parts are equivalent. EAIA equal to T developed omega. So this is the energy conversion equation. Now for generators, you start your input by applying a torque. So you start by applying a torque from a mechanical prime mover. So this torque will produce a speed according to summation torque equal to J acceleration or inertia acceleration. So the motor will start to move. Once the motor starts to move, it will produce EA. It will produce E. According to the equation, EA equal to K phi omega. This EA is generated, it will circulate current IA according to circuit laws, according to Ohm's law. Once you have current, this current will produce torque against, so it will produce torque against the applied torque according to the equation T developed equal to K phi IA. And this will be the reaction, and the right hand side equal to the left hand side. So EAIA equal to T omega. So this is step 3, step 4, and step 5, that you will have a torque against the applied torque. And this is the story for motor and story for generator. And what we studied now is the electromechanical relations. So this is what we called here as electromechanical relations. Now let's sketch the equivalent circuit. So what is the equivalent circuit for the machine? So the equivalent circuit for the machine will depend if this machine is permanent magnet or electric magnet. So if the machine has an electric magnet, or if the machine has a permanent magnet. So if the machine has an electric magnet, so we will have two terminals for the field. So we have a resistance R field, and we have two terminals for the field. And you will be supplying this field with a current I field. And as we mentioned, I prefer to sketch a coil in the field circuit, so you understand that its main function is to produce flux phi. And then I will sketch the armature circuit. So there is a voltage generated EA, then you have the two brushes, and here is the shaft. Okay, so here is the shaft, and the armature has a resistance R armature, and it has a current I armature. So this is the equivalent circuit if you have an electric magnet. So you have two terminals and you are injecting a current here called I field. So you have the field circuit, and here you have the armature circuit. So you have two circuits. If the machine is permanent magnet, as you can see also here, that I prefer to sketch the field making 90° with the brushes, okay, which is the basic design idea for DC machines. If the machine has a permanent magnet, the only difference will be in the field circuit. So here is the armature circuit is the same. So we have EA, speed omega RA, and this is the armature circuit. And for the field circuit, just we sketch a coil, and this coil is producing flux phi, and there is no terminals here, okay, no terminals, no current in the field. So the field circuit, there is no current or resistance in the field circuit, just it's a permanent magnet. It is generating flux phi, and this is the current IA. So here there is no current in the field. This is the only difference. But in most of our cases, we will consider an electric magnet case. And for both circuits, we can use the machine equations, that this EA here, this EA here is constant flux omega, and the torque, if it is a motor, this is T developed. So as you can see, if it is a motor, T developed and the speed are in same direction. If it is generator, the relation between the torque and speed will be opposite. Okay, so this is very important note. So for motors, the torque coming from the machine is the one that is moving the machine. But for generators, the torque coming from the machine is actually a response or a reaction against the main torque, as we saw here. So this torque, the developed torque, is against the torque that is moving your speed. So this torque here is the input torque that is moving the speed, but your induced torque from the generator is against. So for generators, when we sketch speed, so the developed torque is against the speed. For motors, when we sketch the speed, the developed torque in the same direction. As you can see here, the T developed is the torque is generating this speed here. So these are the directions for motor, and these are the directions for generator. So EA equal to K phi omega, and T developed equal to K phi IA, and the third equation that T developed omega equal to EA IA. So these equations are very important equations, and these equations are the machine equations, and these equations again are very, very important. So machine equations are so important. Here is a note. The relation between IF and phi. So don't forget, if we have an electric magnet, how we are creating it. So we will have a pole, and around this pole we will add a coil. This is a coil, and we will supply this coil with current IF, and it will produce flux phi. And we can calculate phi from IF using the magnetic circuit analysis we did in our magnetic circuit chapter. So we can say that phi equal to NIF divided by reluctance. So if we sketch the relation between IF and phi, we are expecting a linear relation, then we have the nonlinear zone, then we have saturation. So if we assume that we are in the linear zone, so we can say that the flux equal to K magnetic circuit multiplied by IF, because it's a straight line equation. And this K is a constant, which is N divided by R, reluctance. So this constant is simply N divided by reluctance, and if we are in the linear zone, the reluctance is constant, so phi equal to K magnetic IF. So if we go back to the equation that EA equal to K phi omega, we can write it as K, and phi is K magnetic IF omega. And we can do this assuming linear magnetic circuit. And this will be the case that we will consider in this course, that the magnetic circuit is linear. So we can write that EA equal to K magnetizing multiplied by IF omega. And if you multiply two constants, you will get a new constant. So we can name this constant as K motor, for example, Km IF omega. So we can write EA as function of phi, or we can write EA as function of omega. So EA equal to K phi omega, or if we assume linearity, EA equal to K motor IF omega. Similarly, we can say that T developed equal to K phi IA, or we can say that T developed equal to K motor IF IA. So this is for linear circuits, and this is for linear circuits. And instead of keep naming the names as K magnetizing, just from the units you can know what is this K is. So if we are saying that for the machine K equal to 0.5 volt per Weber radian per second, or K equal to 0.5 volt per ampere radian per second. So from the unit here, you can see it is given as volt per flux and speed, omega, radian per second. And here it is given as volt per ampere radian per second. So you can see here the unit for K is volt, here is flux, and here is speed. Here is the unit for K is volt per ampere radian per second. So you can say that this is K and this is Km from the units. So from the units you can know which equation you should use, using the exact equation or using the linear equation. So the exact equation is true for linear and non-linear, but the linear equation is only true for the linear case. Okay, so we can write down the final machine equations. So machine equations, I need you to know these equations because these equations are very important. That EA equal to K phi omega equal to K motor IF omega, T developed equal to K phi IA equal to K motor IF IA, and T developed omega equal to EA IA. So these are the three electromechanical relations or electromechanical equations, and these equations are so important. Okay, and here is the equivalent circuit for the machine for both cases, for the electric magnet case and for the permanent magnet case. So